Our last section is going to be on numerical integration. And as I mentioned, there's a lot of integrals for which you can't find an antiderivative. And if you can't find an antiderivative, then you're going to be really stuck trying to figure out, well, what's the area between this function and the x-axis in this interval. So there's a lot of different ways you can try and find that area with numerical methods, approximating it with the midpoint rule, the trapezoid rule, or Simpson's rule. Now let's take a look at each of these. So the midpoint rule is pretty much exactly what you would expect. So what you're going to do is divide up your interval into some rectangles. And then to find the area of those rectangles, you need to figure out where you're going to measure the height. So let's add in some rectangles. Now, in this case, if you divide up this interval into 3 different rectangles, let's do 4 because 4 works out nice and evenly. If you divide it into 4 rectangles, then the width is pretty easy. We're using a uniform width. That width is just going to be the distance along the bottom. But where are we measuring the height of these rectangles? Yeah, in the midpoint. The point that's right in the middle of each of these two endpoints. So that's your midpoint rule. It's just going through and calculating those areas. Now, I'm not going to say this is a lot of fun. It's not. It can get a little bit easier if you do other things. So in particular, we can use something called the trapezoid rule. And let's understand what's going on with the trapezoid rule. Again, let me dial things down a little bit. Maybe just go down to 2. So what the trapezoid rule is going to do is it says, all right, I'm going to form a trapezoid in each of these little intervals that you're working with. So right now I'm just working with 2 intervals. The first one is 0 to 3, and the next one is 3 to 6. And in each of these intervals, you're going to grab the endpoints and form a trapezoid. Now this doesn't really look like much of a trapezoid. This one's a better trapezoid. But we'll find the area of this trapezoid and add it up to the area for the other one, which we'll consider to be a trapezoid, even though it's technically not. Now, the object of one of our exercises earlier this semester in section 5.1 was to say, well, how can I make my approximation better? Can anyone reach back to section 5.1 for their memory there? How do we make our approximation better in terms of the numerical methods we used back then? Yeah, add in more intervals. So if I add in more intervals like this, then yeah, that looks like a better and better estimate. Less and less gap between my function and all these trapezoids. But this becomes kind of a pain, right? Because you have to calculate the area of all those trapezoids. And you might remember the formula, it's 1/2 the height times B1 plus B2. That becomes kind of a problem. But there's good news here for you. When you industrialize this, when you make this full strength and want to come up with a nice formula, you actually can. And here's that formula. If you're going to approximate it with a trapezoid for, say, n intervals, then you're going to want to take the length of each interval divided by 2 times the function evaluated at all these points. Now, the thing to realize here inside this is that when you're working inside here, these function values have a pattern. It's going to be 1 times the endpoint plus 2 times all these interior points until you get down to the last one. So the coefficients inside here have this pattern of 1, 2, 2, 2, 2, 2, all the way down to the last one, which is a 1 again. And it makes it a reasonable thing to do, to calculate at least for small values of n, to do this by hand. So we're going to practice 1 for the trapezoid rule, and we're going to go back and redo this for Simpson's rule, and then maybe we'll compare it to the exact answer. Tony?
Under what pretenses would you use this over like just substitution?
I think the idea here is that we want you to understand just a little bit about how some of these things are calculated. because if you get answers that don't make sense sometimes, maybe you'll take more of a critical look at your function and try and figure out what went wrong. But I mean, it's not something that I personally put a lot of emphasis on. I mean, look, this is what my master's work was in. I really like this stuff, but I'm not pushing it on you guys at all, because basically your graphing calculators, Desmos, all kinds of things do a wonderful job at this. You would never, ever really do this by hand. I'm just showing you a few examples just so you have an idea of how some of this stuff is done on your graphing calculator, because when you plug something into your calculator and hit fn int, it's not finding an antiderivative and saying, oh yeah, the antiderivative of x squared is x cubed over 3. It's doing things in a more souped up version of what we're doing right here. So, all right, so let's bang out a couple examples. We're going to start with, let's see, this function. We're going to do the trapezoid rule for six subintervals. So that's where your n equals 6 is. And let's see how that goes. So, example A. Got the interval from 3 to 6 of the sine of the square root of x dx. Now, we just don't have the machinery to find an antiderivative for this. So, yeah, bummer. You've got to do something else. And that something else in this particular case is to use the trapezoid rule. So let's take kind of a quick look at the graph here, because I have no idea what that graph is actually going to look like. So, Desmos, graphing calculator, y equals sine of the square root of x, and that's going to be between 3 and 6. And, oh, I think it might need to be capitalized. Sine? No. Sine. There. There we go. So not a really dramatic function. Not a whole lot of change. Should be pretty easy to work with. Let's make that a little bit darker. One more time on that. There we go. All right, so there's our function. We're going to have to break that up into some subintervals. And let's see what that's going to look like. Let's see. 0, 6. 6. Okay, so trying to do this to scale, that's 3, 4, 5, and 6. I guess I should probably switch over like this. And I'm just worried about the graph up here. That's all the function that I'm worried about. All right, so not a wonderful rendering, but not horrible as well. If n equals 6, that's the number of rectangles. But how many points am I actually dealing with if I have n equals 6 rectangles? 1, 2, 3, 4, 5, 6, 7. So there's 7 points that I have to deal with in order to work with those 6 rectangles. So let's take a look back at the formula. There's a couple things we need to know. First of all, we need to know the width of each of those intervals. So that's your delta x divided by n. Let's see, trapezoid rule. So that's going to be delta x over n. or delta x is a minus b over n. So delta x for us is going to be 6 minus 3 divided by 6, which is going to be your 1/2. Okay, so that's going to be your 1/2. That's your delta x. The formula for Simpson's rule looks like this. We're going to have t sub 6 equals delta x over n, or excuse me, delta x over 2, times, in this case, it's going to be f of 3. So it's just the value of the function at the endpoint, plus 2 times f of 3.5, plus 2 times f of 4. And these 2's continue all the way through the rest of your problem, 2 times f of 4.5, until the last one. So with this last one, there's no 2 out in front of it. Just like this one over here, it's just f of 6. So those are the values we have to calculate. And there's just no nice way to do this. You just gotta get your hands dirty with this calculation. This is gonna be 1/2 over 2 times f of 3. Now when you're evaluating this function, f of 3, f of 3.5, etc., there's one thing you have to keep in mind. Does anyone know what it is? When I find f of 3, if I'm using my graphing calculator, what do I better make sure I've got going for myself? Calculus is done in radians. There you go. Calculus is done in radians. If you have your calculator in degrees, it's going to mess things up entirely. Drew?
After you show the graph, will you show how you got delta x?
Sure. Let's take care of that now. So delta x is just the length of the interval. So the length of the interval is 6 minus 3 divided by the number of rectangles I have, which is 6.
Okay.
Okay. So I've got to plug in all these values, f of 3, f of 3.5. I've got to find all those values. Some of those have to get multiplied by 2. It's kind of a pain, I won't lie. Let's see. So one way to do this, at least to find the values, would be to plug in your function and then go to the table. And I want to evaluate things at 3, 3.5, 4, 4.5, 5, 5.5, and 6. And there you go. Those are all the values that I need. There's just kind of one real drawback about this, and that is you got to copy down all those values and add them up and multiply by 2, etc. Kind of a pain.
Sure, there's
Should we-
a fancy way.
Should we? Do you want to see a fancier way to do this one?
Well, I assume the calculator has some.
It's
No?
not. Well, it is. It's just something I figured out for myself. I don't know if that was designed this way, but it'll work. So I need to take 1 times this value plus 2 times this value, etc. It becomes kind of a pain. So let's take advantage of something that we did a while ago. And let's see. Out front here, in front of my summation, I'm going to have a 1/2 divided by 2. So let's put a 1/4, or how about we'll put 0.25. Let's put 0.25 times, and I know I need to know the function evaluated at 3. So hit the vars key, y vars, and then press enter twice. That's y1, and put a 3 in parentheses behind it. So that'll evaluate it at 3. And then I want 2 times y vars evaluated at 3.5, and so on. And so there's no way around it. It's just a lot of grunt work. But this to me seems like the least painful way because I don't have to actually type in those values or copy down those values. So 1 and 1, and so on. The only pain is, you know, typing in all these parentheses and stuff like that. So race me, see if you can beat me. Bars, y bars, 1, 1, 4.5.
If we didn't want to write them down, could we do that if we wanted to? Just
You can write them down, sure. I mean,
look on this little thing up.
yeah, I mean, what I'll do when I finish this is I'll go back and figure out what the sum is in between, so you can check your answer versus mine. Y bars, 1, 1, of 5, and 2 bars, y bars. So hopefully the recording on this comes out, because I know it might not be easy to keep up with this in class, but if you can pause it at home, then maybe that'll be a little bit easier to work with. Finally, y vars, 1, 1. Now this last one, make sure it has a coefficient of 1. 6, and bam. So if you're curious, what was the total before I did all that work? You should have had 10.06 something, 0.062. Yeah, 10.062 for a final answer of 2.51552. So, okay. So that's one way to do things, is with that. Out of curiosity, let's compare that to fn int. So let me clear that out. Let's see what the above answer there would look like compared to fn int, see how close we are. So math, 9, integral between 3 and 6. Now instead of typing in the function, I'm just going to type in the y var. So vars, y vars. And then you're still integrating with respect to x. So let's see how close we came. That's not too bad. 2.515 versus 2.517. That's pretty good considering we only used 4 rectangles. So not bad. What makes this a better approximation is that the function is pretty nicely behaved in this interval. It's not bouncing up and down real crazily. It's not bad. So, all right, comments on the trapezoid method. Drew?
Actually, no.
Eli?
I'm confused. Is the Simpsons rule part of the trapezoid method?
No, Simpson's rule is a totally different rule. We'll go over that after we, this is the trapezoid rule.
Okay, because you wrote down.
Yeah, I did write down all 3. We're not doing them in the order that I necessarily wrote them down. Start out here, we'll do this one,
Okay.
and I'll debate if I do want to do this one or not. So,
Okay.
all right. So yeah, this is the trapezoid rule. So I called this T sub 6 because it's a trapezoid rule applied to something with 6 rectangles.
Gotcha.
Appreciate it, thank you. So, like I said, this is pretty good. You know, that's not a bad answer considering that trapezoid rule is pretty rudimentary. But then there's Simpson's rule, which is going to step this up a little bit. So let's see, this is 5, 6. Let's try this again with Simpson's rule. Now Simpson's rule has a different approach to things. And it's a much more clever approach. Instead of just fitting a rectangle there. Let's see, where's, instead of just fitting a rectangle in an interval, here's what Simpson's rule does. And let me see if I can't dial this down to maybe a 1, 2. All right. What Simpson's rule does is it takes your interval and divides it up into, it takes your intervals and it fits a parabola in these intervals. So it takes this point, this point, and this point, and it fits a parabola to those curves, and then it finds the area of those curves. So here it is. It's finding a parabola between here and here using those 3 endpoints, and then it finds the area underneath those curves. And then it does the same thing over here, finds the area between the curve and the x-axis underneath another parabola. And it industrializes this in a very clever way. So the amount of work done for Simpson's rule is about the same as the amount of work done for the trapezoid rule. It's just that Simpson's rule turns out in general to be a lot more accurate.
I have a question.
Yes.
So you mentioned earlier Gauss.
Gauss, yes.
Was the one to make this?
I doubt that he was the first one to do this. I have no idea who first created this. Yeah, Gauss did have the normal distribution, was called the Gaussian for a while, but I don't think he was the first one to discover Simpson's rule or trapezoid. Simpson's rule might be one of those things like Pascal's triangle where Simpson's name is associated with it, but he didn't really discover it. I mean, Pascal's triangle goes back, I mean, literally centuries before Blaise Pascal was ever even born. So this might be the same way with Simpson's rule or not, I'm not sure. So Simpson's rule, you can kind of see a lot of the same stuff going on. You've got a different coefficient out in front. Instead of a 1/2, you've got a 1/3. Delta x is the same thing as it was before. It's that length of the interval divided by the number of subintervals. So it's the length of each subinterval. The only thing that's really different that you need to really pay attention to is the pattern of coefficients. Inside this bracket, the pattern of coefficients is 1, 4, 2, 4, 2, etc. And it always ends with this symmetric 1, 4, 2, and then 2, 4, 1. But other than that, it's pretty much the same thing. So we'll do this with Simpson's rule. So Simpson's rule, we'll call it S sub 6 for Simpson's rule. It's going to equal delta x over 3. And then it's going to look like this. We're going to have an f of 3. And I want to kind of really highlight the coefficients here. So let me do it this way. F of 3. Leave a little space here. F of 3.5. Leave a little space. F of 4. A little more space. F of 4.5. And then F, leave a little space. F of 5. F of 5.5, and finally F of 6. So the pattern of the coefficients goes 1, 4, 2, 4, 1. 1, 4, 2, 4, 2. So it's going to keep on alternating that pattern. So it's going to look like this. 1, 4, 2, 4, 2, 4, and then 1. The outside terms, kind of like the last example with the trapezoid rule, they get a 1. So it's very similar to the last one. Delta x from the last one, delta x is going to be 6 minus 3 over 6 again, so it's going to be our 1/2. So S sub 6 on us is going to be 1/2 over 3 times all this. Now I'll let you choose it. Do you want to do this one by hand? Or do you want to do it on the calculator like we did with the last one? Calculator? All right, so get out your calculators. We'll do this one on the calculator. You can do it by hand. You just got to copy all these numbers down, f of 3, and then multiply by 1, f of 3.5, multiply by 4, etc. Does anyone need to borrow a calculator? We're all good there? All right. So I'll do it from scratch, even though there's a large part of me that's saying, you know, I can just hit second and then enter and go back a couple calculations and clean things up. But I'll do it again from scratch. That way it gives you a chance to follow along. Let's start out by cleaning things up. You know what? I'm just going to do the part in parentheses first, and then I'll divide it by 6, which will take account of that coefficient. So we'll start out with vars, y vars, function evaluated at 3, plus 4 times vars, y vars, evaluated at, let's see, evaluated at 3.5. You know what? I'm not liking this. And it occurs to me, I think there's a faster way to do this. Let me see, if you hit the alpha and then the window key. No, is it alpha, zoom key? One more.
Use the arrow to like move it over. Yeah.
There we go. If you hit the alpha and the trace key, then you get to that Y1 a little bit faster. So, yeah, that's probably a better way to go here. Let's see. 1. Yeah. All right, so one way or another, you got to find your way to Y1. Let me show you that little trick again. So we need 2 times Y1 here, so it's going to be 2. You don't need to hit the times key. To get to Y1, you can do alpha and then the trace and press 1. That's a little bit better. I'm liking this better now. Plus 4, alpha, trace, 1, 4.5. Oh no, I forgot a parenthesis. So, more little tricks here for you guys. Did you know you can insert something? If you hit the second key, then the delete key, that takes you up here. You can insert. And let's see, I need to do a couple more here. Plus 2, alpha, calc,
So we're doing this
and then
the original problem.
5 plus 4, alpha, calc.
We still didn't sign this first.
Oh, I did it again. No, I'm okay. Parentheses, 5.5. And finally, the last one is plus alpha, calc, by 1, parentheses, 6. Phew. 15.0169.
Times 1/6.
Yep. So out front here, you've got the 1/2 divided by 1/3, which is 1/6. So 1/6 times this is simply dividing this by 6.
106.
106. Oh, thank you. Thank you. 2.517. I think that's better than trapezoid method. 106.9. Thanks. So a little dyslexia there. I took care of that. So the final answer here is 2.5178. Let's compare that to the exact answer one more time. Let me go back and find that one. Bam, bam. That's really, look at how good that is. 1, 2, 3, 4 digits of accuracy. So down to the nearest 10,000th, that's really good. So Simpson's method is a lot more is a lot more efficient, a lot more bang for the buck. Yes, sir.
I'm assuming on an exam, like on an exam, if we did this, you wouldn't be asking for an exact answer, would you?
No, this is not an exact answer problem. No. Trying to think. The other thing about making an exam problem like this is that I would make the number of intervals really small. 6 would be the outside maximum, probably more like 4. Yeah, no, I'd be very, very careful about putting a problem like this on the exam. Anything else? Now, for those of you who think that, you know, I'm mean and I teach a tough course, I really try and be as fair with my problems as possible. One thing that I could do on these types of problems is make you find an error bound. And the error bound calculation is a little bit of a pain. I mean, the b minus a cubed over 12n squared, that's all easy, but this k here is going to be the maximum of the second derivative function on your interval. So that becomes a big problem. It's just to figure out, well, what's the maximum of the second derivative on that interval? Yeah, have fun. That's for the trapezoid rule. For the midpoint rule, it's a little different. Simpson's rule is actually the best in this regard because Simpson's rule can actually integrate cubic polynomials exactly. So that's pretty good for something that only deals with parabolas. All right. Comments or questions on this one? How many of you actually managed to get this number off your calculator? Really? All right. That's pretty good. Good job. All right. Let's shut this down and then call it a day. Section 6.7 or 7.7.